Dear students, we are back with the lecture series on the course material of Transportation Engineering 2. Today's lecture is based on the jointed or the welded rails. What we have seen in the previous lectures, especially the previous two lectures, is that there are certain reasons due to which the rail sections which are provided on the track gets eroded or weared out or damaged or they fail out. Now, looking at all those aspects which we have discussed previously, what we found is that the joints are those points which are the points of weaknesses and which causes number of wears or tears or the damages which start from these particular points. So, we are going to discuss today's lecture about the different aspects related to the different joints as well as the welded rails and their advantages. In this lecture, the lecture has been defined as rail joints, the welding of rails, advantages of welding rails, short welded rails, long welded rails. Now, coming to these rails and the joints of these one, we have of course discussed about number of factors which are the problems which are caused at any of the rail joint. We will be trying to look back again on all those factors which we have discussed previously under different lectures. What we have found is that the joints are the weakest link in a track. This is a point of discontinuity, and because of this point of discontinuity and the gap being provided between the two sturdy rail sections, what we found is that whatever load is coming at this point is unsupported in nature, and that is why this is one of the weakest link in any of the track. Another thing is that there is a break of continuity in the two directions. It is a break in the horizontal direction as well as in the vertical direction. Now, when there is a break in the horizontal direction, it is going to create certain amount of jerk, and because of these jerks the discomfort will be stimulated. Now, if this discomfort is there, so everybody will be feeling that there is some sort of a pushing behavior which is coming from the track. Whereas, in the case of the vertical direction also, this break of continuity causes the loss of stability. So, this is another aspect which needs to be taken care of when we are designing or devising the joints. Now, one more thing which we have seen when we have discussed the wear of the rail sections at the end of the rail, what we have found is that there is a blow of wheels at the end of the rail section, and this has further resulted in the wear. Now, looking at the same aspect in this case, because we are talking about the joints, what is happening is that due to these blows of the wheels at the ends of the rail sections, the fish plates gets loosened out. At the same time, whatever other accessories or fastenings being provided at that location will also be coming out of their shape. Some of these things are like ballast pad or the fastenings which are trying to keep the system at the place. It may be in terms of the metal plates which have been provided below so as to disperse the load to a wider area or support the joint. We are looking at the different types of the joints a little further in some of the slides. So, we will be looking at some fastenings which have been shown which tries to support the joint systems. Then there is another aspect is the wear and tear of track components. Now, because as we have seen that there is a break of continuity and this is resulting in the impacts or the blows which are coming to the rail section from the top, that is the moving loads, it finally results in wearing of the surfaces. This wearing of the surface may be at the topmost surface of the rail head section or it may be on the end section of the rail head. So, this is another aspect which is to be taken care of, and if propagates in any of the direction, then it may also create an effect on other track components like sleepers or the ballast being provided below this joint so as to keep the joint in place. Then the distortion of track geometry is another aspect. It depends on the type of the forces which have been applied at this joint and their direction and the final result of those impacts. Now, if there is no space, there has been a movement of one rail section with respect to the other rail section, then obviously it is going to distort the track geometry. and in that sense it may also result in the buckling of the track. So, this is one type of distortion which may be there, or there may be some other distortions like the formation of kink at the point where the two rail sections are getting joined. So, this is another sort of a distortion to the track alignment. Now, because of these reasons, the movement of the rolling stock on that type of section will become a little hazardous, and it will not be safe enough. At the same time, it will also be creating discomfort to the passengers, or maybe a discomfort or jerks to the freight which is being moved on that section. Further, when we look at the impact of the rail joint, what happens is that because it is going to create an effect on all the components which have been provided at that rail joint, it reduces the lifespan of all those components, and these components are nothing but they are the rails, sleepers and fastenings. So, it means the periodical maintenance which is required to be done after a certain period of time, instead of that time period we have to do it beforehand. So, this is another aspect. It is going to create an effect in terms of the monetary value, because it will be increasing the maintenance cost of the system, it may be increasing the overall cost of the system. Then another aspect is the noise being created because of all those features which we have discussed so far. Whatever sort of deformation, distortion of the track is resulted due to the problems of the joints or due to the certain movements of the different components of the joint, then it is going to create a noise in terms of the interactions of the rolling stock with these static measures, that is reels. So, this is another problem at the joints. The more noise is created as compared to the continuous sections being provided on which the rolling stock is continuously moving. And finally, it is also going to result in the higher fuel consumption. Now, in this case what is happening is, because as we have seen that there are so many things which are happening at the rail joint in terms of the problems, in terms of the wears, in terms of the impacts, it has its effect in the form of higher consumption of the fuel also. And this is another aspect where the economics needs to be taken care of, because the final value or the total amount which is to be incurred for the operation of this system or the operation of this track increases. So, these are some of the problems which are associated with any of the rail joint. So, on the basis of all these problems, whatever we have seen, what are the requirements of the rail joints that we will be looking at? In this case, the very first thing is that we have to maintain or hold the rails ends for continuity. There should not be any distortion, there should not be any formation of the kink at the rail joint, due to which the rail ends are not continuous in nature and they are going out of the shape, that is what we can say, or they are going out of the alignment with respect to each other. So, this is one aspect that we have to try to maintain, or we have to try to hold the rail ends at the same level, at the same location, so that the continuity of the rail section is maintained. Another aspect is the sufficient strength and stiffness should be there. Now, in the case of the rail joints, because the two rails which have been placed one after the other on the same alignment, on the same path, they have been jointed together using fish plates and fish bolts. Now, in this case, when we are joining these by the fish plates and fish bolts, then these fish plates and bolts have certain amount of strength or the capacity to bear the stresses, and that is from where the more strength or stiffness is coming in at the point where the two rail sections have been jointed together. So, this is how a sufficient strength and stiffness can be maintained in any of the joint section, because otherwise it is a weakest point and it may break down, or there may be any other problem associated at this level. Another aspect is adequate expansion gap. Now, this is related with the length of the rail section which is provided on the two sides of the gap or the joint. In most of the cases, if we are using the rail sections as being manufactured by any of the company, then may be around 13 meters in length in the case of the broad gauge. So, at every 13 meter there may be a gap, and then there may be a gap at every further distance which is taken in terms of an expansion gap. What is happening is that, as we have discussed again before also, it is an effect of temperature change. All the rail sections or the tracks which are laid at any point of a time, they are laid with respect to certain temperature. If there is any difference with respect to this temperature, that is the temperature of the surrounding is either more or lesser, that is going to create the effect in terms of expansion or contraction of the rail sections. And these expansion gaps needs to be provided so as to take care of all those expansions or contractions which are taking place in the rail sections because of the difference in the temperature. So, this is one of the aspects which needs to be taken care of. If the expansion gap is not adequate, then obviously it is going to create a jam condition of the joint, and then further if there is a movement, it will result in kinking or it will result in buckling of the rail sections. At the same time, if the expansion gap is very large, then it is going to create a higher amount of impact on the next rail section depending on the direction of movement of the rolling stock. Therefore, in both the cases where we are talking about a wider gap or we are talking about a lower gap, it is going to create a problem. So, that is why a certain amount which is being provided as far as the variability or tolerances are concerned in the gap needs to be provided. The other aspect here is, because we are talking about the joints and the certain sort of fastenings have been used so as to join the two rail sections as well as join the rail sections below. One thing which is to be taken care is easy removal or replacement of the different components or the materials. Now, at the section where the joint is being provided, most of the time there may or may not be a support being provided. In Indian conditions, we are providing the joints which are not being supported. So, in that case, it is being supported by the ballast cushion which is being placed around the sleepers or below the sleepers. So, if we have to remove this material, then it should be easy to do that, or if we have to replace it, then that should also be easier. At the same time, the flexibility should be there so that as and when it is required, that work can be done from the maintenance point of view. Then provision for wear at the rail ends has to be made. It means that whatever wear is going on, we are not going to change or replace the rail section as soon as the wear has started. We have seen in the case of the wear that there is a certain amount or percentage by which the wear is allowed as far as the weight of the sectional weight of that component is concerned. Maybe it is head, maybe it is the overall rail section. So, in that sense, we can wait up to that point up to which those wear has occurred, and then after that there is a requirement of changing or removing or renewing of the rail section. So, the provisions have to be taken care in this way. Then adequate elasticity has to be there, because we are talking about the strength and stiffness. Then it should not result in a condition where there is a movement of the two rail sections because of the loads which are coming from the top. Now, in this case, as the load comes on one rail section, it is going to get you can say deformed towards the downward direction, whereas the other rail section which is being jointed to this one will remain in its position. Now, as soon as the rolling load moves from this rail section to the other rail section, it is going to deflect in the downward direction, whereas the previous one should come back to the normal level. If it is not coming to the normal level, then there will be undulations being created into the track, and these undulations, as we have seen previously, are going to create or cause the stresses in the track. So, therefore, there should be adequate elasticity in those components which are joining the two rail sections at this point, and that is how the total elasticity of the system can be maintained. And then, as we have talked about the cost component or the economics, the initial as well as the maintenance cost should be as low as possible, and that is going to be happen if there are lesser of removals or replacements required, or the periodic maintenance of the system required is not short enough, it is to be done in a longer time period, then only we can sustain in this case. So, therefore, as we have discussed about all these requirements, now we can look at the various types of the rail joints. The rail joints can be provided in terms of, or they can be classified as according to position of the sleeper at rail joint, or it may be done in terms of according to the position of the rail joint, or there may be some special joints, there may be insulated joints, or there may be welded joints. So, these are some of the type of the rail joints which are in general provided globally depending on the requirements of the tracks. So, we will be looking at all these joints one by one. We start with the first one, that is the according to the position of sleeper at rail joint, and this category also again there are further classifications or categorizations of the different types of the joints which can be provided. In this case, we can look at the first joint, that is the supported joint. The supported joint means in this case the joint is supported directly on any system, mostly a sleeper, and the rail end becomes slightly high. What happens is that as you have seen that in the previous cases all those rail sections have been supported with the sleepers. Now, as soon as a sleeper is being provided below the joint, then it causes some amount of change in the level of that rail sections at the joints, and that is it is going a little above as compared to the normal level of the rails. And the wear and tear of a sleeper and maintenance, these are the some problems associated in this case, because what happens is that the load which is being transferred to the joint is directly coming to the sleeper, and when it is directly coming to the sleeper, then the whole of the load is going to be dispersed through that medium. And in the previous case, when the sleepers have been provided below the rail sections, then the load is coming through the rail section. So, some of the load is being taken care of by that section, and then finally a reduced load comes to the sleeper. So, it means in the case where the sleepers are directly being provided below the joints, there is more of wear and tear of the sleepers. At the same time, if that sleeper is to be taken out, then first of all of the system has to be removed, all fastenings have to be taken out, and then only it can be maintained, renewed or removed. So, that is another problem associated in the case of supported joints. One example of this type of a joint is a duplex sleeper. We can look at this aspect in this one. Here in this diagram, this is one rail section and this is another rail section, and this is a joint in between these two rail sections. In general conditions, what happens is that there is a sleeper being provided below the rail section in this case as well as in this case, but if a sleeper is provided at this location where the joint is there, then it is known as the supported joint. So, this is one type of the joint available. Another type of joint is suspended joint. In the case of suspended joint, what happens is that some portion of the rail will remain as a cantilever. Cantilever, as you have read in the strictures, it is a part of the system which remains suspended in the forward direction away from the point of support. So, in this case there is a problem of loosening of packing at the joint. What happens in this one is that because of the loads which are coming at this one, and because the joint is not being supported, the loads will directly going to be dispersed to the ballast, and when these are going directly to the ballast section, then in that case because of the loads, that ballast will start coming out of its position, and that is the one reason of the loosening of the packing at this level. But in most of the cases we are providing the suspended joint, so that is why it is one of the commonly used joints throughout. In this diagram we are trying to look at the same sort of a joint. This is a rail section being provided, and this rail section is having a joint at this level. This is the joint. So, in this case the one sleeper is provided just before this joint on this rail section, and another sleeper is being provided after this joint on the other rail section. So, in this case this is the total amount of rail section which remains suspended after this support. At the same time, in this case also it is going to remain like this, and this is what is a cantilever section. So, there is no support being provided at this point. Only support which is available at this point is the ballast or the cushion, which is being provided as a packing on the sides of the sleepers or below the sleepers. So, that is why the load is directly coming to the ballast cushion here. So, this is what is suspended joint. Then another type of a joint is known as bridge joint. Now, in the case of bridge joint, we use a metal fillet or corrugated plate which bridges the joint, and that is why it is termed as bridge plate. So, we look at this one. In this case, this is one rail section being supported on the sleepers, and this is another rail section being supported on some of other sleepers, and here a plate is being provided in form of a arch, and this is how this joint is supported. There is another case where instead of providing it in the form of an arc, then this is a plate being provided as a sort of a bearing plate, and this is embedded here in this sleeper and on this side in this sleeper, and that is how it is supported at this level. Now, because of this support, whatever load is coming from the top will get dispersed by the wider area of this plate, and it will go to the sleeper as well as to the ballast cushion being provided at the bottom. So, this is bridge joint. Then another one is on the basis of position of the rail joint. In this case, the first type of a joint is the square joint. The square joints are mostly used on straight portions, and this is one of the most common type of the joint which is provided on the railway tracks or the permanent way. What we see is that this is a square joint where these are the rail sections being provided. This is all these are the rail sections on this side as well as on this side, and the joint is provided at this location. It means the joint on the other rail section being laid parallel at the gauge distance is going to be just opposite side to this one, and that is how at every regular distance we are going to have a joint on both the cases, this rail as well as this rail, and this is why they are termed as, because this is making a sort of a square condition. So, this is why they are termed as a square joint. Another type of joint in the same sort of a condition is a staggered joint. Now, in this staggered joint, this is mostly provided on curved tracks. In the case of curved tracks, what is happening is that there is a larger distance to be traveled on the outer curve as compared to the inner curve. This is what we have seen already when we have discussed the coning of wheels or when we have discussed other features. So, in that case, whatever is the rail length being provided, the rail length is a constant rail length, and if you use the same rail length, because of the difference in the distance being traveled on the two tracks, the joint will be coming at different locations, and that is why it is termed as the staggered rail joint. Now, this staggered rail joint, as we see in this case, the length of the rail section remains constant, it is not changing, but because the distance traveled on this one is more as compared to this one, so the joint is coming at this location with respect to joint which is coming at this location on the inner rail, and this is how they are not opposite to each other, and they are termed as staggered rail joints. Then there are some special type of joints. One joint which is known as base joint. In the case of base joint, we use a flat or corrugated plate, and these plates are bolted to the sleeper using some bar type of inner fish plates or angle type outer fish plates. What happens in this one is that there are two types of fish plates being used. There is an inner and outer fish plates. Outer fish plates are of angle shape, and that is why these outer fish plates, they come out and then they are bolted to the sleepers, whereas the inner side of the fish plates which are provided on the gauge face, they are of bar type. They simply just adhere to the surface of the flanges of the rail sections. Then another type of a joint is known as compromise joint. Now, this compromise joint is provided at those locations where the combination fish plates are provided. Now, we will be looking at this combination fish plate when we take up the rail fastenings, but just to mention here is that these combination fish plates are provided at those locations where the two rail sections which are being joined together, they are of different sectional areas. So, in those cases the normal conventional fish plates are not provided, and instead the combination fish plates are provided, and at that location the joint which is provided is known as compromise joint. Then there is an expansion joint, as we have discussed. It is provided so as to take care of the amount of expansion taking place in the rail sections because of thermal stresses. There are insulated joints being provided in the locations where we have to just stop or remove the flow of the current. So, what we do is that some sort of a filler is being filled at the joint level. Then there are welded joints. Welded joints are those joints where the two rail sections are joined together by using a weld. So, instead of some sort of fastenings being used like fish plates or fish bolts, we will be using the welds. So, those are the welded joints. We will be looking at these welded joints in further detail. Now, the joints needs to be avoided at certain locations. What are those locations? The level crossings. Wherever the level crossing is being provided, that is there is a crossing of a road and a rail section at the same level, at that level the joints should not be provided at that position. Another one is if there are short bridge spans, then in that case also on the bridges the joints should not be provided. Then approaches of the bridges, the reason behind in these two cases is that if the joints are provided at the bridge level, in the case of the short bridge spans, then whatever stresses will be induced because of the impact condition at that position due to the rolling stock, that may create problem, that may create some defects in the bridges. Those are the smaller bridges, whereas in the case of the approaches of bridges, again for the similar reasons of stresses being induced, we try to avoid the joints. Then there is another location at the end or center of the span of the long bridges, again the joints should be avoided. Now, what we have seen is the different types of the joints where there is a beam connected together using fish plates and fish bolts. Now, as we have seen, whatever is the condition, whatever type of accessories we use, there remains the points of weaknesses. So, one thing is that we have to remove those points of weaknesses as far as possible, and one way of doing that is the welded rails. So, in the case of the welded rails, there are certain advantages. What are the advantages we look at is that it reduces the maintenance cost. Now, the jerks which are being induced due to those joints, or there is a requirement of removal of the components which are provided at the joints because of the continuous wearing of those components. In all such cases, the maintenance cost is involved, whereas as soon as we have welded the joint, therefore, there will be a reduction in the maintenance cost, and this amounts to something like 20 to 40% of the total amount. Then there is another aspect is the reduction in the creep. Now, as we have seen that there is a longitudinal movement of the rail sections due to different reasons. Now, this longitudinal movement is going to be resisted by the fixtures which have been provided at the bottom of the rail sections, and these fixtures are their connectivities with respect to the sleepers. Now, if we can increase this sort of a resistance or the friction which is induced by the connectivities or the fixtures which have been provided between the rail sections and the sleepers, or the number of sleepers which have been provided at the bottom of the rail section, then probably the creep can be reduced further. So, if we are having the welded rails, then this is another possibility that we will be having a big rail section, and that big rail section works together so that the frictional resistance will increase, and this increased frictional resistance will reduce the creep. Then it will also be increasing the strength. because there is a discontinuity and the forces which are acting at this point of a discontinuity are directly going to the ballast section, and therefore, there is a sort of further wearing of the ballast section at that level, and which results in the loosening of the ballast section. In this case, when it is being welded, there is no such transfer of the load to the lower levels, which are having a lesser of a strength as compared to the higher levels, that is the rail sections. So, it means as soon as the two rail sections have been jointed together, it is going to increase the strength, and there will be lesser points of weaknesses available on the overall rail section, overall track. And then it also dampens the intensity of high frequency vibrations, because as we have seen that the points are not there where there will be some impact taking place. So, due to that reason, as this is being welded together, that is going to dampen that frequency vibration. And obviously, as the reduction in creep is there, as there is lesser requirements of maintenances, as we have increased the strength of the total section, obviously this is going to result in the increased life of the rail section. So, these are some of the advantages of welded rail sections, and this in this case, when the life of the rail section is increased, obviously finally it is going to reduce the overall cost of construction as well as overall cost of maintenance of these tracks. So, once we have got an idea about what are the advantages of any of the welded rail sections, then we will be looking at the different types of methods by which the welding can be done between the two rail sections. Now, there are four in general methods: gas pressure welding, then we have electric arc welding, this is also termed as the metal arc welding, then there is a flash butt welding, and finally there is a thermite welding. So, all these welding processes which are available, they have been used at different point of a time globally, depending on the requirements, depending on the facilities available, and then they have their advantages and disadvantages with respect to each other. We will be looking at what is these type of weldings and what are the relative advantages and disadvantages of the flash butt welding and the thermite welding in the coming sections. So, as we have seen that we have four methods of welding, we will be looking at all these four methods one by one. The first one is gas pressure welding. In this case of gas pressure welding, what we do is that we use two types of gases, oxygen and acetylene. They are used together maybe in two different cylinders, and then at a temperature of 1200 degree centigrade, this is the amount of temperature up to which we have to go, at which the two rail sections which have been butted together to each other, the metal will start just flowing and it will become one section. So, this is what is done in the case of gas pressure welding. This is one of the cheaper way of welding, and it is also resulting in good quality of weld, but what is being observed is that there are some limited outputs only which are available in our conditions. Then there is another method, electric arc welding or metal arc welding. In the case of this electric arc welding or metal arc welding, what we do is that the two butting sections of the rail, they are treated as two different terminals, where the electric current will be passed through these two terminals across the gap. Now, this electric current may be passed using different methods. The methods are the insert plate technique, or Sharon process, or the enclosed space technique. Using any of these methods, we can do this electric arc welding or metal arc welding, though this metal arc or electric arc welding is again is lesser in use. Then next of the two methods, that is flush butt welding and a thermite welding. Here in this chart, a comparison of these two welding methods as well as their principle has been laid down. What we see is there are certain points on the basis of which we can make a comparison between these two welding processes. The very first thing is that what is the principle of welding in those two cases. In the case of flush butt welding, what we are doing is we are passing a 35,000 ampere electric current between the two rail sections so as to join them together. Whereas in the case of the thermite welding, we are using an exothermic chemical reaction between the iron oxide and aluminum, and this exothermic chemical reaction, what happens is that we get iron and aluminum oxide, and this is the principle by which the joining is being done. Now, as far as the quality of weld is concerned, the quality of weld is quite good in both the cases, and of course, it is a little better in the case of flush butt welding as compared to the thermite welding. Then if we look at the strength of the weld, the strength of the weld is to be taken or is to be considered in terms of the repeated loads which are coming from the top at that section and the behavior of that joint where this welding is being done. And this is what is termed as fatigue, and it is observed that the flush butt welding locations, they are good in fatigue, whereas the thermite welding is weak in fatigue. Then there is a total time required for doing a welding at any location. In the case of flush butt welding method, it is taking 3 to 6 minutes per welding process, whereas in the case of thermite welding condition, there are two time periods depending on the type of the method being used. There is one conventional method and the other one is a short period method. So, in the case of the conventional method, it takes around 30 to 45 minutes time period, whereas in the case of shorter method, it is taking 10 to 12 minutes time period. So, in this case, generally a preheating is done so that the time is being reduced in the thermite welding process. Then further, some more points are there on basis of which a comparison can also be done between the two same welding processes. In the case of flush butt welding, the welding is to be done in the workshop. Maybe this workshop is maintained at the site level, where in the case of thermite welding, it can be done at site. That is, wherever the track is being laid, we can go to that position and we can weld the joints wherever they are available. The cost per weld is around 400 to 600 rupees in the case of flush butt welding, but it is higher in the case of thermite welding and ranges between 700 to 1200 rupees. Tolerances are very tight in flush butt welding, so it means that the variations are very less permitted, whereas in the case of the thermite welding, they are the normal conditions. And the control on quality is it is the control being done by using a welding recorder. This welding recorder has a flexibility of recording the process of the welding, wherein whatever parameters are there which needs to be maintained, they all get recorded. It may be in terms of the pressure, it may be in terms of the load being applied, or it may be in terms of the temperature, etc. Whereas in the case of the thermite welding, there is no such monitoring possible. So, that is a type of a combination, the type of a comparison between the two types of the welding processes, and what we found is that the flush butt welding process looks like that is of course cheaper, but at the same time is also providing a better quality of weld as compared to the thermite welding process. Now, based on these welded sections which have been provided, the overall tracks which are being jointed can be again classified. They can be classified as short welded rails, and short they are termed as SWR, or these SWR or the short welded rails, they are in general a combination of 3 or 5 or 10 rail lengths which are welded together. It means if you are talking about the 10 rail lengths welded together in a broad gauge condition, it is going to transform into 130 meter rail length, whereas if we talk about an individual piece, it is 13 meters rail length. So, this is how we have removed the number of joints in this case. And in this one, the contraction of the expansion takes place throughout the entire length, and this obviously this contraction or expansion is because of the temperature variations, and therefore, it means there are excessive thermal forces which will get set in the whole of the length of the rail section. And in Indian conditions, as we have seen that there are the variations of temperature going from very low to very high conditions. So, in that sense it is observed that the short welded rails of more than 3 lengths, they are going to produce much higher thermal stresses. And so, as to remove these conditions where the higher thermal stresses are there, due to which there will be higher level of expansion, and it will be creating a problem of kinks, or it will creating a problem of buckling of rails. So, these have been limited to 3 rail lengths, and they are not being found technically and economically feasible for maintenance also. Then another case is a long welded rail case. In the case of long welded rails, what we are doing is, this is of course again termed as LWR, and this is based on the theory of expansion and contraction. In this case, we are having more number of rail sections being jointed together. It is more than obviously the 10 rail sections which have been jointed at the maximum in the case of the short welded rails. Here we are trying to look at the total amount of expansion or the total amount of contraction which is going to take place in the number of rail sections which are jointed or welded together. So, based on the amount of expansion and contraction, the length of the rail section is to be decided. Now, here whatever expansion is taking place, this expansion is going to be a function of the coefficient of linear expansion of rail material, the length of the rail section, and the temperature variation. The higher is the temperature variation, higher is the expansion in the rail section. And if this coefficient of linear expansion of the rail material is higher, then also it is going to create higher level of expansion in the overall length of the rail section. Then further, it is going to be proportional with respect to the rail length, and therefore, again in this case the expansion will be more if the length of the rail section is more. And that is one of the reasons why the short welded rails in Indian conditions, as we have seen previously, have been restricted up to a length of 3 rail sections. Now, in this sense, how we can control or how we can decide upon what should be the total length of the long welded rail or LWR rail section. And here the free longitudinal movement of the rail is restricted due to fastenings and ballast cover provided, as we have seen previously, that there is certain amount of resistance which is going to be offered to this movement or this expansion of the rail section, and this resistance is coming through the accessories which have been provided between the rail sections so as to connect them to the sleepers. So, in this case what is going to happen is that these fastenings or fixed features will be creating a resistance. At the same time, the ballast which is being inserted or packed on the side of the sleepers, that will also be helpful in creating a resistance to the movement. So, there are certain amount of resistance which is trying to restrict the movement. So, this restriction or this amount of free longitudinal movement is to be measured with respect to the resistances being offered by the track itself. So, this restricted expansion or contraction gives rise to accumulation of thermal stresses in the rail metal, and this accumulation of thermal stresses in the rail metal is going to decide that what should be the length of the rail section. So, in this length of the rail sections, there are certain locations where these rail sections should not be provided. What are those rail sections? The new constructions. Now, whatever new railway track is being laid down, as soon as the load start coming from the top, there is a readjustment of the material which is provided at the bottommost layers. These bottom layers are the ballast cushion and the subgrade soil or the formation level on which the ballast cushion is being placed. Therefore, there will be a certain amount of settlement which may be taking place because of the heavier loads which are coming repeatedly from the top. In such condition, if there is any problem associated with the rail occurs, then the whole of the long welded rail section has to be removed if the LWRs are provided. Therefore, what is being suggested here is we have to wait till the section stabilizes, and as soon as the section stabilizes, then that section can be converted to the LWR section, that is the long welded rail section. Another case is the locations which are requiring frequent renewals, like the places where there are more of corrosion, corrugation, wear, etc. What happens in these cases, like as we have seen in the case of locations near the coastal areas, or we have also looked at the locations like tunnels where the wear of the surfaces or wear of the overall rail section is more as compared to the other locations. So, in all these locations the long welded rails cannot be provided or should not be provided, because if you are doing that, then the renewal or the maintenance problem will be there. Either you have to cut down the section, remove the section and again weld it, or it is better that you have a smaller rail length, remove whatever is the affected rail length, and that is how it is maintained. Corrugation is another aspect which is location specific. It is not that it is happening everywhere. So, that is why whatever locations where the corrugation is taking place, we can remove or rectify those locations, or we can renew those locations, and if we have to do it with the long welded rails, then it will not be possible again. The next thing is the weak formations. In the case of weak formations, as we have discussed before also, that it is related to the conditions of stabilizations of the stability of the railway track. We have to look at the amount of deformation which will be there. If the amount of deformation is very large, then obviously we have to go with the smaller rail sections. If the soil is susceptible to pumping, that is, it is getting removed along with the gradients being induced in the any of the direction, then in those cases also there will be a settlement taking place as the loads are applied from the top. So, these are the other locations where LWRs are prohibited. Then further, those locations where heavy contamination of the ballast takes place, like the locations where there are industrial area where the effluents are coming and they are contaminating the ballast. So, if such type of locations are there, then the life of the ballast is going to be affected, because there will be some reactions which may take place. So, at that locations also LWRs are prohibited. The another location is the location where there are chances of floods, there are chances of breaches or subsidences. Then the locations where the curve radius is less than 500 meters, or where the reverse curve is being provided with the radius of 1500 meters or more, in those cases also the long welded rails should not be provided. Then the long welded rail should also not be provided based on the gradients, and the steepest gradient permitted is 1 in 100. So, these are some of the locations on which the LWRs cannot be provided. Now, the higher category of LWR is termed as CWR, that is continuous welded rail section. This continuous welded rail section may be of a length more than 1000 meters, and at times it may be from one station to the other station. What happens is, in the case of the short welded rails, as we have seen, it is having a length of up to 130 meters, whereas in the case of long welded rails the length may go up to a length of 1000 meters. Now, this is a further category where the length can go more than 1000 meters, and even there are sections where the rails have been provided in welded condition from one station to the other station, means going to certain kilometers continuously. And this is based on locking up of longitudinal thermal stresses. As in the case of the LWR, we have seen that there are certain amount of resistance which is being offered by the track, and this resistance is trying to resist the movement of the rail section in terms of expansion of the rail. Now, we have to look at what point those thermal stresses get locked. As soon as this amount is there, this length is available to us at which the locking has happened, then the rest of the section is going to be free of the movement, and this is what is the concept behind this one. What happens is that it has a tendency of removing the points of weaknesses such as the switches or the buffer joints which are provided along. And in this case further, on the Indian Railways it is recommending that the conventional insulation joints or turnouts are left out and they are provided after 1000 meter of LWR, as LWR is having a longest section is 1000 meter. After every 1000 meter we can provide the insulation joints, or we can provide the switches so that the turnouts can be maintained. And of course, in this case these require heavy maintenance. Then these continuous welded rail sections, they have been used on the German railways and British railways without any switch expansion joints, which are provided in the case of LWR we have discussed after every 1000 meters. In this case the sections are running from one station to the other station throughout without any switch expansion joints. So now we are going to look at the length of the LWR sections. This is going to be governed by the thermal forces, as we have seen previously. This thermal force is given by F is equals to alpha T A E, where alpha is the coefficient of expansion per degree centigrade, T is the rise in temperature above the temperature at which the rail is being laid, A is the cross sectional area of the rail section, and E is the modulus of elasticity. The values of certain constants are also being shown here. So on the basis of this value the thermal force can be computed, or this value can also be computed by a formula like 31.5 S into T, where S is the sectional weight of the rail section and the T is the temperature by which it is increasing. So in this case what happens is that the resistances forces which are being induced by permanent track has to be considered with respect to the thermal stresses, and the point at which the two are going to become equal, that is the point at which the locking of the stresses will be taking place. It means as the length of the track increases, the resistance will be increasing. So we have to go along the length of the track and we have to find the point at which the thermal stress is equals to the resistance offered by the track, and this resistance is coming through the sleepers and their connectivities with the rail sections. So this expansion continues from the end of the rail towards the center, and this stage is going to be reached where the resistance offered by the track structure is equals to the thermal force created due to change in the temperature. So as soon as this stage will be reached, what happens is that there is no movement which is taking place beyond this point, and this is what is this is termed as the locking of the stresses, and this portion of the LWR at the end which goes under goes movement due to temperature variation, and this length is termed as breathing length. So this length which is being taken is something around 100 meters from the end of the rail section in the case of the broad gauge track, whereas in the case of the meter gauge track it is around 150 meters length. So on the whole, if we are taking about any this LWR section, it means in the broad gauge condition the 200 meter rail length is there which is going to be affected because of the temperature stresses, or there is a 300 meter rail length which is going to be affected by the rail thermal stresses. Any length more than this one is not going to be affected by the thermal stresses, and therefore there will not be any movement in that section. So due to this reason, with this concept, the longer sections of the rails have been used as a continuous welded rail sections which are going even to a distance more than 1000 meters in length. So this is a concept behind the different types of the welded rail tracks, that is SWR, LWR or CWR rail tracks. So we have looked at the different types of the joints, maybe the simple joints in terms of the position or in terms of the location, or we have also looked at the types of the welded joints and the ways by which the weldings can be done in the today's lecture. So we will be stopping at this point, and we will continuing with the another thing related to these tracks in the coming lectures. Thank you and goodbye.
you.